Hi, I'm Kate Compton, and I'm presenting Lost in Possibility Space Adventures in Genetic Algorithms for ASYNC October. You may know me better as Galaxy Kate online. I'm at galaxykate.com and at GalaxyKate on Twitter. I've done a whole bunch of different procedural content generation works. I've done 5 years on Spore and SimCity. I'm now more than 5 years into a PhD in generative games and creativity tools for casual users. And I do just a ton of different generative apps and prototypes. You can find these at galaxykate.com. Um, but I've done projection artworks. I've done artworks that you control with the leap motion with your hands as the watercolor painting bot, procedural dance generators, flocks of generative butterflies, generative trains, and even generative plants. So I like to think a lot about procedural content generation and how to explain procedural content generation to other people. One of the things that's helped me a lot with my own practice is thinking about procedural content generation and generativity in general as a kind of pipeline. It's a way to take one piece of data and transform it a number of times and through a bunch of different transformations into a different kind of data. To take one piece of data and expand it into a piece of generative content. What this tends to look like is you have some input and there's some sort of complicated procedure, and at the other side pops some content. I've written about this at length in a paper called The Generative Framework of Generativity. You can look that up online and read it yourself if you'd like to know more about this. But for the most part, what I'd like you to get from this talk is that procedural content generation is a sort of pipeline. If you're looking at procedural content generation in games, it's often even more complicated. There's perhaps some sort of machine learning or user actions, a simulated ecosystem, or a random seed, and you might be generating such diverse things as difficulty or terrain or characters. I wanted to create a generative framework of generativity. That is, a framework that I could use to not only think about generativity, but construct new examples of generative pipelines, I guess. So some of the things I was thinking about were, what are the basic components of generativity? What are the inputs and output conditions of those components? And then, most importantly, how do we chain those components together into complex pipelines? What are the basic Lego pieces of generativity? And then once we have these pipelines completed, once we have a pipeline that takes one kind of data and turns it into some other generative form of data, how can I take that pipeline and use that pipeline as another part of a generative pipeline? This framework comes out of my past experience in the games industry and also the ways that I've been looking at a lot of the procedural content that gets shipped in games. When you look at a full-size AAA or very large indie game, or even a finished indie game that gets shipped to users, it's very rare to have a finished ship system that doesn't use a whole bunch of different techniques chained together. Even when we ship toy generators, often you'll have one central technique and a lot of other techniques to help that technique look good. By the time the system reaches a user, it'll actually have a lot of different generative techniques all chained together. We'll see this in No Man's Sky, in Minecraft, and especially in Dwarf Fortress. Dwarf Fortress is a huge a huge stack of lots of different generative algorithms. So what generativity is, or at least how I'm defining generativity, is that it's a pipeline of successive data transformations. Each transformation either generates or transforms or prunes away information. So there will be a whole bunch of different cards all stacked together, taking some piece of information and turning it into a different kind of information. A generator is a pipeline of these data transformations. You know how I mentioned Legos earlier? If I have a whole set of these Lego transformations, and I know how they can all socket together, it should be possible to design a generator that generates generative pipelines. That'd be pretty cool. That's why this is called the Generative Framework for Generativity. And in fact, I did end up making this. It's a pencil and paper activity, or rather it's a deck of cards, a physical deck of cards, that are called Generaminos. You can read more about them in the paper listed at the bottom. But what they are is it's a set of cards that each card is a transformation of data. So it takes some data from the top and transforms it into the type of data that's down below. And you can use these to build complicated branching pipelines. So here's an example of a diagram of a procedural content generation art piece or art installation that I made called Idle Hands. What it does is roughly it takes input from a leap motion, so hand tracking. That gives you joint positions, which are vectors. I can then get the graph nodes from those vectors, which are points, and then I can use the Voronoi diagram, which takes points and turns them into regions, and then I can draw those regions on a screen. So this makes a real-time interactive leap motion piece with some sort of interesting crystalline motion that you can gesture at with your hands. Using generaminos or just designing a generative pipeline, imagine now you have a pipeline. In the paper that I mentioned earlier, I talk a lot about the different kinds of categories of transformation. So if you're wondering what different ways of data transformation are there, you can read that paper for more information. But for this talk today, I'm going to talk about what happens once you have a pipeline. There are different ways that you can interact with generative pipelines that can create really different user experiences, but I'll be talking about these today. So search-based techniques, brute force optimization in genetic algorithms, but also user exploration, which I think is one of the most interesting ones. Often we treat generative pipelines as a sort of magic button that we can press. We press a button and some content comes out. This is almost like a little capsule toy box where you turn the knob and you're going to get a different kind of content each time. So I'm going to re-roll a random seed, and then I'll get some interesting piece of content out. I can press the button as many times as I want, and I can get lots of different content. Another thing that we can do with that is we can make a genetic algorithm. You can read much more complicated genetic algorithm tutorials online. There's a lot of scholarship around these and genetic and evolutionary algorithms in general. But I won't go into that complexity. I'll just give you the very simplified version of it. And strikingly enough, it uses it uses generative pipelines. It's going to use 3 pipelines. So you're going to have 3 different pipelines that turn one thing into another thing. The first pipeline is to grow something. So you're going to have a pipeline that takes some sort of DNA and generates an individual out of it. You can imagine this like taking the compressed DNA in a seed and growing it into a plant, so you can actually see what the real plant would look like. You can do this with really lots of different algorithms. The algorithm itself doesn't matter as long as you have a pipeline that takes some DNA and turns it into an individual. The DNA and the individual will depend on the project that you're working on. So pipeline 2, judging. This takes an individual or a population of individuals and then generates a score, survival, or rankings. So you could say that the user decides which one that they like best. So this is a very simple pipeline where it just shows an individual on screen and the user upvotes it or downvotes it. The third pipeline is for reproduction. This is where you're going to take as input the DNA of the winners and possibly any ranking or scores, and somehow you're going to transform that into new DNA, mutants and children. Of course, there are a lot of different ways to do this. Biologically speaking, there's crossover, there's mutations, asexual reproduction or sexual reproduction, where you take 2 parents and create DNA that's a combination of those 2 parents. Only our own biology, and you have a lot more options. So you can have DNA taken from every successful parent in the entire ecosystem. These 3 pipelines are the only thing you need to create a genetic algorithm. But we see in these pipelines there's this DNA that appears as a variable type in these 3 different locations. So we need to have a representation of DNA. I personally tend to use an array of floating point values. You can learn more about this in my talk, Let It Grow, from ProcJam 2015, which is available online. I like arrays of floats because they're very simple to program and they're very approachable to use, and they have a whole bunch of other interesting properties that we'll see in the rest of this talk. An array of floats is really just an ordered list of numbers between 0 and 1. So, for example, this is a single DNA strand for a single individual. You can imagine these as vectors that you can place on a 3-dimensional cube if your DNA was only 3 units long. Of course, most DNA that's long enough to make interesting content is much longer, so I'm using about 32 individual units of DNA per individual. Now, of course, that's hard to imagine in 3 dimensions, so you have to imagine a 32-dimensional cube instead. But you can still imagine each piece of content as being a position somewhere on this 32-dimensional cube. And so each position on this cube, even in 32 dimensions, is a unique piece of content. So if your possibility space is a 32-dimensional cube, how do you actually start understanding what's in it? There are a couple of projects currently existing, Gillian Smith's Analyzing the Expressive Range of a Level Generator, and Michael Cook's Dinesh, which try to take this multidimensional cube and compress it at least into 2 dimensions that you can look at on screen. As I mentioned before, though, there are a number of neat tricks that you can pull in 32-dimensional space. So imagine we drew some sort of curve through this space. Remember, of course, this is the 32-dimensional curve. But each point on this curve should be pretty close to the other curved points in the curve nearby, which means that each piece of content along this curve should be close to the previous piece of content. And this is going to allow us to make an animation just by dragging a point through this curve and seeing what kinds of content it generates. In addition to creating paths, you can also create landmarks. The classic procedural content generation project Dryad created a number of trees and used those as landmarks to help people guide themselves around a multidimensional space. So you were no longer just moving randomly through space, you were getting closer to an oak or farther away from a cactus. The Facebook game Petals created virtual regions in their n-dimensional space. Each region had a collectible flower in it, and you are trying to explore new regions in this n-dimensional space to collect all the possible flowers. It may be that the way we understand possibility space is similar to the way that we understand physical space. There's a book called Image of the City, which describes how people understand their way around cities using paths, edges, districts, nodes, and landmarks. If you don't have these ideas, you can't understand how to navigate a city. We just saw these same features pop up in understanding possibility space as well. I wonder how far you could push this metaphor. How much could you annotate a possibility space such that there are regions and edges, districts, landmarks, and nodes, such that there are hidden secrets, and when you unlock those hidden secrets, that expands a new possibility space that you can only get to from that one particular node? We can also talk about how to translate possibility spaces into other possibility spaces. So we know that an array of floats as DNA can be used to create individuals, but where does that DNA come from? It could come from a genetic algorithm. But that's not the only place it could come from. Remember, this is just an array of floats, so it could come from another array of floats, such as Allison Parrish's phonetic similarity vectors, which takes words and maps them to long arrays of floats. What would happen if we took every word in a poem and generated trees based on those? You could also take a device that generates interesting arrays of floats, like the NeuroSky MindWave, which generates floating point values representing your brainwave. You could also take a device like the Leap Motion, which generates floating point numbers, although they're in vector form, and somehow translate those to DNA as well, creating trees that when you gestured would change. Locations around the world are also floating point numbers, or can be used to generate DNA. What would happen if you sampled locations across the globe, created DNA based on those locations? Would you have a Pokemon Go for your generative algorithm? If you use frequency analysis to turn music into floating point values, you can even create a music visualizer. Of course, you can also do just a genetic algorithm, so I can select a couple of plants that I like, and then re-roll their offspring, or increase the mutation to create more varied offspring. And of course, if I have DNA, I can display that as either a plant, or I could render it as a face. So here are some faces that I can genetically evolve. I can also take a thin two-dimensional slice of the 32 possible dimensions and graph those. I hope that's given you a lot of interesting ideas and explained what possibility space is and how you can use it in genetic algorithms and more. Thanks a lot for listening. I'm Galaxy Kate Compton.